So there is agreement amongst scientists and between governments that we should limit rising CO2 levels in the atmosphere to 450 parts per million or less if we want to avoid dangerous climate change to society. But at the current rates of increase of CO2, we're going to pass this threshold in something like 20 years. This increase of CO2 is also important to the environment. Indeed, it causes, for instance, a decrease of pH in the ocean, and this ocean acidification is damaging the ecosystems that underlie the food chains in the ocean, such as the carbonate-producing coccolith blooms that you see around Ireland in this picture. We know, of course, what we should do to stop CO2 going up in the atmosphere. We should be decreasing our energy utilisation, and the energy that we do get, we should be taking from alternative energy sources, such as those seen on the board here. This is, of course, the plan A for how we should be dealing with climate change. If plan A is working, what we need to see very soon is dramatic cuts to the emission rate of carbon to the atmosphere. But if we look at the rate of emission of carbon, what we actually see is it's increasing year by year. And after a brief blip during the global recession in 2009, we saw record-breaking carbon emission in 2010. Set against this backdrop, it may well be wise to be thinking and investigating a plan B for how we could deal with climate change. One such plan B is to pump aerosols into the atmosphere, to reflect sunlight back to space, and therefore to cool the planet. This mechanism is rather like the aerosols you see from volcanoes or from clouds, which naturally cool the planet for us. If we could do just the right amount of this solar radiation management, perhaps we could flatten off global temperatures, as shown in this schematic here, and therefore solve global warming. But this would not address the question of ocean pH, and it also locks us into a cycle by which we have to continue to pump out aerosols in increasing amounts to mitigate the increasing CO2 levels. It's also, the effect of global warming on rainfall and temperature, shown by the dashed lines here in this Oxford model, are also not directly counteracted by this solar radiation management, shown by the solid lines here. You get a strong regional overprint when you do solar radiation management, which could readily lead to geopolitical tension about the right level of geoengineering to do. So it would be much better, rather than managing solar radiation, to actually manage carbon dioxide and to remove carbon dioxide from the atmosphere, to flatten off CO2, stop global warming, and also curtail ocean pH change at the same time. One way to do this carbon dioxide removal mechanism is to fertilise the ocean with iron. This figure of the North Pacific here shows you in the hot colours regions where large amounts of biological productivity naturally remove large amounts of carbon from the atmosphere. And highlighted by the red circle at the bottom there, you see a small patch of red, which is where iron has been added artificially and stimulated additional carbon removal in the natural system. At Oxford, we're investigating how this natural carbon cycle works, what are the natural sources and sinks of iron to the ocean, and how does that iron supply moderate the ecosystems that you see here. We're therefore trying to understand whether it's sensible to manipulate the iron cycle and remove carbon from the ocean in this way. A possibly better way of removing carbon dioxide from the atmosphere is to lime the ocean to form a stable bicarbonate product. This is rather like giving the oceans a giant Alka-Seltzer, and it's the technique that we already use to correct for acid rainfall in high-latitude lakes by liming them as shown here. One of the good things about this liming reaction is that it directly locally corrects for the effects of ocean acidification rather than it being a global effect. And this technique might be used topically in regions of particular ecological stress where carbonate producers are struggling with ocean acidification, such as the reef environments of the Great Barrier Reef, shown here. And a third technology we might use for carbon dioxide removal is to accelerate the natural weathering of silicate rocks, such as the basalt shown here, into carbonates, which occurs on the continents already. So the three equations that I've shown you on the board here, each of them works in theory, but I don't want you to go away with the idea that we should start applying these globally around the Earth. I'm not advocating here that we should geoengineer. What I'm advocating is that we should research geoengineering. We should be looking at the science and engineering behind it and considering the legal, governance and ethical issues that underlie manipulation of the whole planet. Perhaps we can find a plan B if we were to undergo this sort of research. One thing that's definitely true about any such plan B is that it will have to be operated on the same sort of scale as our current global energy industry. So it'll be big, it'll be ugly and expensive. It may still, nevertheless, be better than the sort of catastrophic climate change that we will see if we're not able to curtail our carbon emissions and use Plan A in the future. Thank you.
Good job, Jim.